Hey everyone, today's video is going to be done in a slightly different format. I will be attempting to recreate, well, I say attempting, but I've already done it and I just kind of wanted to share how I did it. So today we'll be talking about how we can recreate this effect in the well-known game called Superliminal. So this is what happens in the game. You pick up objects from a small distance, you move it to a different spot by moving your player's character, you'll release the object and you'll notice that all of a sudden the object has changed in size and position. So this is a demo of how this final product will look like in Three.js, completely done without any physics engine or without any special bells and whistles. It's just all pure vanilla Three.js. So there's a ball here and there's a plane. If I walk up to the ball, I can grab the side of the ball, or just anywhere of the ball actually. I can grab the center, I can move away from the plane. You see it's still behind the ball, right? And if I let go of the ball, you'll see that the ball has changed in shape. What I can also do is the inverse. I'll grab onto the ball here, I'll move close to the plane. Okay, I'm going to let go of the ball. Then if I move away, you'll see that the ball has indeed changed into a smaller size. I can do it even more and exaggerate it a little bit, and you'll see that it all works. So I won't be actually going into any of the implementation details over here. I'll just very quickly go through some of the very high level points that I've discovered or that I've experienced, and just some really good concepts to know. And all the implementation details are available. They're just in written form, and you can go to the blog and you can copy and paste code. But if you don't like this view, you can always click on the view full changes link at the bottom of each diff, so each file, and it brings you to the GitHub commit, which you can see the full files in there. You can also click on browse files and it gives you the entire state of the project, so you don't have to manually assemble the pieces to build a functioning project. Every single diff has a functioning project behind it. It's just behind, you just have to go to the GitHub and you can clone it and it's runnable. So this is the core concept behind the illusion, and that is proportionality. So imagine that you have this object here and you want to push the object backwards because, for example, the object is right in front of your camera right now and you want to push it all the way to the back so it's flush with the wall. So what you would do is, using the naive approach, you would take this object, grab it by its handle, and then push it all the way as far as you can. But then, without any form of modification, this would look very abrupt, and you'd be able to see and tell that the object has obviously been pushed backwards. But instead, if we had scaled the object proportionate to the amount of distance the object has traveled, for example, imagine a new object's position is twice the distance the initial object was from the camera. What you would do is you would scale the object to be twice as big as its initial size, and then if you do this correctly, you wouldn't be able to tell that the object has either resized or shifted in position. In fact, here is another image, probably better image to describe this transformation. So this is our initial object position, and this is our final object position here. And the initial one is the green one, the final one is the blue one. So how do you calculate, you know what the distance is that the object has to travel, because we know where the wall is and we know where the object is, so we can kind of tell like what the final position of the object should be. But the question is, what should the final scale of the object be after this movement? And this formula here is just a very simple elementary school level algebra. You take the scale of the initial object, you multiply it by the ratio of the final distance to the camera over the initial distance from the camera. And so this is how you get them. So if the final distance is twice as far as the initial distance, then you would say that the final scale would have to be twice as big as the initial scale. And all that is really the bulk of what this effect is made up of. However, there are a couple of little things that you have to worry about, and it's not as straightforward as that. For example, now this is an illustration of that exact problem. You see this clipping happening here? I'll just wait for this GIF to restart from the start. So we shoot a ray out, it intersects the object and the wall. We find the reflection on the object. We push the object all the way to the wall. But now you see that there's a problem here, and the problem is sometimes the object isn't completely flush with the wall, and there's clipping that happens. And so we kind of do have to pull the object backwards back towards the wall. until the object no longer intersects with the wall. And to do this in Three.js, it's very simple because Three.js provides us with some very nice utility functions, such as, let me find it right here. So bounding box calculations are done very easily using the three.box3 Three.js object. You say set from object, and this computes the bounding box of your target object, and we just use dot intersects to see if those objects intersect, and we continuously pull the object backwards until it is no longer intersecting with the wall. So if you got all of that, here is another challenge or another edge case for you to consider. So consider this. We have an object and we want to constantly reposition the object to our target location, or wherever we want to move the object to. May it be a point on the wall or somewhere closer to the camera, because that's what we want to do. When we hold down the left mouse button, we want the object to come closer to the camera so that it's exactly 1 unit in front of our camera. And then when we release the object, we want to push the object all the way as far as we can until it hits a wall. But the question now is, how do you reposition the objects in a way that doesn't make it snap to and fro abruptly? Because when you set a position of an object, you're actually just setting the center position. So that's like the middle of the ball if the object was a ball, because you're using Three.js's position property, which if you go to object 3 here, you'll see that it has a dot position property, which this is how you modify the position of an object. You change the x, y, and z coordinates of the object. But how do we change it? So how do we grab objects such that we don't just, for example, this is the initial object position, and the moment you grab it, we shoot a ray from the camera, we raycast a ray in a straight line to the object, and then we find the object. But then now, in order to reposition the object, we're setting its center, which you can see this is not a straight line, so this is kind of abrupt. So what you would do is you would instead use the object 3D's hierarchical nature. I have a very good example here I can show you by Sean Bradley, SeanBradleyCode.net, sbcode.net. It's got a very nice illustration here, example code. So this is these are 3 objects. The red one, the blue one is a descendant of the green object. The green object is a descendant of the red object. So the red object is the grandfather of all objects. If I change the position of the red object, for example, see, this is the red object, right? It affects every single object in the same way as if they were all part of the same object. But if I modified the position of the blue object, only the descendants or the children of that green object changes. The red remains unaffected because the red is above the green object in the hierarchy. And similarly, moving the blue object only moves the blue object. It doesn't move the green or the red object because it is the leaf node. It is at the very bottom of this hierarchy. So that's the secret to this effect. You first send out a straight line ray using a Raycaster, and you find the intersection point on your target object. We call this the ball. So this is the target object, and it's a ball. So I'll call it a ball. And then here you create an invisible virtual pivot parent, which is an object 3D by itself. It's represented by this red ball over here, this red circle. And that's an invisible point that we create, which is an object 3D itself. So then we reattach this ball, this target object, to be a child or a descendant of this pivot parent, or the anchor point, or the handle, whatever you want to call it. Then compute the coordinates of that point, which is one unit away from the camera in distance. Then you reposition the pivot parent or the anchor point object to this position. You set the position, the x, y, and z coordinates of that parent object. Then automatically your child ball or your target object will follow the parent to that position without changing the relative distance between the child ball and the pivot parent object. So this is an example animation I've created of the pivot parent. So for convenience, I've drawn a cube around the pivot parent. The pivot parent by itself is invisible because we haven't given it any material or any textures. So I've drawn a helper box, which is the grid box you see over here, which is the pivot parent's location. The problem now, this is the last problem I promise you that we have to solve before we get the fully functioning end product. And the problem is that when you rotate your camera left and right, like if you just pan your camera to look at a different direction, the object appears as though it's swiveling around the pivot parent, right? It doesn't look like you have picked up the object. Ideally, our final product should look like this. You want to hold on to the object, and the object should just be picked up. It shouldn't swivel around. And that's because of a concept called rotation, synchronous rotation. Do you know that movie called Transformers: Dark of the Moon? Well, there was a reason why it's called Dark of the Moon, and that is because the moon always rotates in a way that it always faces the Earth on one side of the moon's surface. So this is a very good example here. If there was a person standing on this side of the moon, every time the moon rotates, that person's head will always be facing towards the Earth. And that just comes as a result of the moon rotating around the Earth while rotating around itself at the same time. It's called the counter rotation. So you'll never see the other side of the moon, and the moon will always show us the same face. And this is kind of what we need to accomplish here, because let me just go back to this side here. This is your object and this is your camera. So imagine that there is some stuff going on here in the back of the object, right? Once I pick up the object and I move my camera around, I want to never be able to see the back side of this object. I want to always have my camera be facing towards this very same side of the object. So here my camera has turned, what is this? This is 45 degrees. So now the camera is looking completely to the right side. If you don't rotate the object and the object stays upright, it would look like this, and now I'd see this part of the object, which I was never able to see before. But if we apply that same counter rotation, or actually it's not really a counter rotation, it's the same amount of angles that the camera has turned. So the camera here has turned 45 degrees from its initial orientation. We also take 45 degrees and apply it to this object in a similar fashion. So the object rotates the same number of degrees as the camera does. So now what happens is from the camera's point of view, it's the same side of the object, and I'm never able to see anything past that or the back of the object. Now there are some Quaternion math involved in this if you're using quaternions to manage the object's orientation and transformations, but that's all like not too hard, and it's also a little bit technical, more technical than I want it to be in this video. And the TLDR is that you would treat quaternions, if this is your first time working with quaternions, you would treat them the same way as you would treat matrices or transformation matrices. And if you want a detailed explanation, be sure to check out this article on the blog. It's in the description of this video. So there you have it. That's pretty much everything that you need to know to be able to implement such a project in Three.js without any physics engines or any fancy bells and whistles. You can just do all of this in vanilla Three.js. And be sure to read the docs if you're actually going to attempt this. If not, I hope this has been helpful or at least somewhat interesting. Until then, see you in the next one.